My name's Nick Terrel, and today I'm going to be talking about atomistic uncertainty-driven data generation and the ANI neural network potentials. I like to start off all of my talks in a sort of similar way, where in computational chemistry we have just this inherent balance between accuracy and computational cost. And in any system that we're interested in, we have to choose the level of detail that we apply to that system in order to study it. Generally, we're striving for a chemical accuracy of about 1 kilocalorie per mole. That's been like a long-standing goal in computational chemistry. There are many methods which don't reach that level of accuracy and are still helpful, but that's just a general goal. And here I'm showing a few methods on the red line of different approaches in computational chemistry to solving problems, ranging from sort of this might irritate some people in chemistry, but low accuracy methods like force fields, which show no bond breakage or formation, but are very good for large systems and use classical mechanics, ranging all the way up to coupled cluster methods, which are explicit representations of every electron in a system to approximate solutions to the Schrodinger equation. The ANI neural network potentials have been around for, about 8 years now. And these are neural network models which have a computational cost that's similar to that of force fields with approximately linear scaling, but we can approach the accuracy of QM methods based on the training set that is used in producing these models. So the nice thing about neural network potentials is they're able to reproduce the behavior of QM data at very large speedups, but these approaches are limited by the generation of data and the uncertainty quantification. Once we have a trained model, how can we actually tell whether it's right or wrong? If the whole point is to not compute all of this QM data, we want to have some good predictor of whether or not we're getting a good answer when our model makes a prediction. So first about ANI, I want to talk about the potential of neural network potentials. In the ANI method, these are high-dimensional nonlinear functions which iteratively learn to predict the shape of a QM potential energy surface, so how atoms in a system interact with one another at different bond angles and distances. The nice thing about neural network models is that there is no need to input knowledge about the functional form of a potential energy surface. We, in order to get a prediction, we don't pre-train ANI with any sort of understanding about electronic behavior or anything like that. It's all representative or represented in the data set. But this means that we need a large comprehensive data set. And in order to get a good working model, that means that you need a very large amount of data to properly train and validate a neural network model. ANI-1 in 2017 showed that it's possible to reproduce DFT energies and potential energy surfaces at the omega B97X level of theory about 1 million times faster than you can produce those, computing them in the traditional path. And now I want to walk you through just a brief overview of the steps that ANI takes in order to make a prediction. We start with an input of species and coordinates. So if you look at this little diagram I have here, it's just a 2D representation of atoms in a simulation where every atom in the system is treated as a central atom to look in some cutoff radius at what neighbors are surrounding it in order to identify the chemical environment. Those species and coordinates of the central atom and its surrounding neighbors are passed to what we call our AEV computer to compute an atomic environment vector. This is a fixed size vector that's used as the input to our neural network potentials. For every atom in the system, those AEVs are passed through a species-specific atomic network. So carbon has its own network, hydrogen has its own, et cetera. And from the atom-specific networks, we get an output of a raw atomic energy. And we call this a raw atomic energy because it's a value that doesn't really have any physical meaning, but you can think of this as a deviation from the ground state atomic energy. And so for every atom in the system, we get that deviation from the ground state, and we add to it the energy of a, for example, carbon atom that's just isolated in space, and we pass that through what we call the energy shifter to make these more real values that are closer to the QM computed energies. And it's important to note that we started doing this energy shifter thing as a replacement for biases in the training of our machine learning models, and it works very well actually, because before, when we weren't using this energy shifter, we had this tendency to get sort of nonsense answers whenever you had like incomplete valences and atoms that were isolated in space, and now we have kind of solved that problem by treating these things as they are, an atom that's alone until it has neighbors to interact with it. And so then the total energy of a molecule is computed as the sum of all of these atomic contributions, and then the very last step that we take in getting a prediction is we look at not just one model, but an ensemble of neural network potential models, and we calculate the standard deviation across those models and normalize it by the system size to get what we call the QBC. For as long as ANI has existed, really, this has been the measure of reliability that's used to determine whether we can trust the prediction that ANI is giving or not. And this is going to be the focus of the first half of my talk. But first, I want to give a bit of a practical example of what the AEV looks like for a real system. So if you have this peptide where I've highlighted that yellow atom, if you can see it, say that's the atom that we're interested in for a specific AEV. Its nearest neighbors are the ones that fall within this sphere, and everything outside of that is invisible to that central atom. And so what ANI does is to try and capture chemical behavior by isolating just the local behavior, only what its nearest neighbors are doing. And without getting too technical, this isn't a perfect approach. There is more that really goes into having an accurate chemical representation, where there is some long-range interactions that we're looking into adding to our potential models. But for small organic molecules, this has been shown to work pretty well. But we use this QBC that I mentioned earlier to improve on the accuracy of ANI while using less data overall. So ANI-1 that came out in 2017 was sort of revolutionary, but it was much too large. The data set was about 22 million conformers, shown here. This red dot is, this is a broken scale, but 22 million conformers, and it had an energy RMSE of about 11 kilocalories per mole. So, an order of magnitude larger than what we were hoping to achieve. So the ANI-1X and 2X data sets were created using an active learning process, where we start with a small subset of the ANI-1 data set and train a model to that small subset, see what molecules this QBC test passes or fails, and then add new data iteratively to achieve better accuracy. This QBC can be thought of as a binary classifier, where we plot the energy errors and all of the QBC values against each other, and we try to capture all of the errors above 1 kilocalorie per mole, and that corresponds to a QBC value of 0.23. So that number doesn't really mean much physically, but for the training sets that we have, this is what we consider the cutoff point for whether or not an ANI prediction is trustworthy. This worked pretty well for going from ANI-1 to ANI-1X, but I have some concerns with the way that the QBC works, and I want to demonstrate those with a fairly simple example. And that's the size dependence of the QBC. As I mentioned, it's the standard deviation divided by the square root of number of atoms, and that means that if you have a very large system, that can influence whether or not the this uncertainty quantification is trustworthy or not. So if you look at this first molecule that I'm showing is a pentane ring with this epoxide over here, and the QBC value of this huge long alkyl chain molecule is 0.223, which is just below the threshold of what we consider like a good prediction. It passes what we call our QBC test, and if you truncate that alkyl chain, then suddenly you're far above what is considered a trustworthy value. And it's important to note that in both of these structures, I'm using the exact same 3D geometry for the pentane and epoxide parts of the molecule. The only thing that's changing is the alkyl chain. What's really leading to this issue, if I can move my mouse right, is this epoxide. We have some of those in our ANI training sets, but when we sample new data, we're just taking structures that we already have and creating new conformations of those structures. We're not actually sampling new configurational space. We're only sampling new conformational space. And I think this serves as a nice reminder that we named it after this guy. He's kind of evil. So if the ANI neural network potentials are really predicting the atomic energies, why don't we just use those to calculate the QBCs? Again, just as a reminder, the energy of a system is found as the sum of the atomic energies plus those ground state atomic energies that are added in for every atom. And what the neural networks are actually finding are these atomic energy contributions. So for another practical example, I have this methane molecule, and I want to go through really only the first two, but I'm going to show you the values that are produced by our 8 models. So here you have some, again, these are physically meaningless, but they help demonstrate a point. This is the carbon energy contribution, and then this is the hydrogen energy contribution for each of these 4 hydrogens in this model. And this sums to 11.8 kilocalories per mole. This is before adding those ground state atomic energies. If those seem like very small values to you, that's intentional. And then when we look at our second model, suddenly we have a 19 kilocalorie per mole difference between the carbon energy prediction between the 2 models. However, the sum is almost exactly the same. These 2 models are predicting that the energy of this molecule is almost identical, but they have no idea what the energy contribution of each atom type should be, and that's a trend that continues for every one of the 8 models. There's no consistent basis for how atomic energies are predicted because, again, these are not physical values. They don't have any meaning in quantum mechanics. This is just something that our model produces in order to get to an answer. All that really matters is the sum of the total energy. And so when you look at the standard deviation of these values, there's, not only a huge difference between the carbon standard deviation and the hydrogen one, but they're both bad, and the total molecular energy is predicted with a high level of certainty. So atomic energies really just, we've done a few things to try and make them more consistent, and we get worse total molecular energy predictions whenever we change something. So that hasn't been a great approach. And just to demonstrate this point a little bit further, this is a test set of the first molecule of each molecular formula in our training set that I'm showing on this diagram on the left, and another one that'll pop up on the right. But here, the methane energy prediction is a very low uncertainty energy prediction. It's all of our models agree almost perfectly on what the energy of this molecule should be, but whenever you look at the carbon within that molecule and compare it to all of the carbons in that same data set, the model has no idea what the energy contribution of this carbon should be. And this is an issue that we don't want to change the way that our model works entirely, but we need some other way to think about atomistic uncertainty. And so we want to try and quantify model uncertainty. Doing that is pretty easy. You create a benchmark data set that has systems that you're interested in. So for ANI, we're interested in small organic molecules and some small biomolecules, things like that. And the Comp6 V2 data set was designed specifically for benchmarking this 2x potential. But the issue really comes in with how can we quantify and reduce uncertainty that is not model dependent? So this is kind of 2 questions. How can we adequately and efficiently sample chemical space, and how do we know which regions we're undersampling? What things are we not representing in our data sets in order to get the behavior that we want out of our model? And lastly, using the QBC as we have been for the past few years, we risk oversampling the same chemical environments because, again, we're not adding new configurations of atoms. We're just adding new conformations of atoms, changing the shapes of the ones that are already in our data set. So we're just adding a lot of data that looks the same and hoping to get better answers out of it. So we've started thinking about what other approach could we take. And ANI2X is not only trained to the QM molecular energies, but also to the atomic forces of each atom in the system. Most of our molecules or in the training sets are off equilibrium structures, so things that have atomic force components that are pointing in some direction or another. And the ANI models have done a very good job at predicting these atomic forces, and we've been using these to look for insight into model understanding of local atomic environments. Like, is there a way to say, our model doesn't know what it's looking at because the atomic force predictions by the ensemble have this level of uncertainty. And so another important thing, unlike the atomic energies, these are a physically meaningful value. This is, it's saying the atom wants to move in this direction to be nearer to the equilibrium value. But, so this nice looking figure is on the y-axis is the ANI predicted magnitude of atomic forces, and then comparing that to the QM, like actual value that it's training to, and it's a near perfect prediction. But the range of values that these things have vary greatly. So it's not so simple as just looking at the standard deviation of the predictions of atomic forces, because most of the forces for near equilibrium structures are going to be near zero numbers. But if you pull an atom very far off of its equilibrium position, it's going to have a high force component that's trying to push it back into the right position to be in equilibrium. So we want a normalized measure of uncertainty for these, atom level predictions. Standard deviation is a nice measure of distribution, but it's not great for comparing things apples to apples when they're very different conformations. So the, first thing that you think of whenever you're normalizing a standard deviation is to look at the coefficient of variation. Computing these, we had just some issues with very small values being divided by very small values, leading to a large number that makes this not such a great predictor of uncertainty on the atom level. And instead, we've been looking at what we call the relative range of predictions, where, again, we have 8 models within our ensemble. We take the largest force magnitude prediction and the smallest force magnitude prediction, find the difference between those two, and if the range of predictions is, at least equal to the mean, so if we drew a red line right here, we would consider that these are not very good predictions of forces. And as far as why would this be useful, what we're looking for is we want to identify where are the ANI models predicting energies and forces poorly when we don't actually have the QM data to compare it to. The whole point of neural network potentials in chemistry is let's do fewer computations but still get reliable answers. We want to reduce the computer time to solving these computations of systems that we're interested in, and we don't want to have to compute everything explicitly. So identifying high ANI error prediction or high error predictions by ANI is a challenging thing, but uncertainty quantification helps us to identify these things that fall into this region where our QBC might be very low, but we still have high energy error structures that are in this region. It doesn't give us an actual error to find the uncertainty of our predictions, but it does help us see if the networks understand what they're looking at so that we know what sorts of structures we should add more to in our data sets. And that's all the talk I'll do about the QBC, but now I want to talk about how can we sample predictive uncertainty a little bit better. And so this is a project I've been working on recently with Dr. Jinza Shui. He graduated from our lab earlier this year, and he's been working with NVIDIA now. And sort of the capstone of his doctorate was to do this massive simulation that we call the early Earth simulation. He used basically all of the Hypergator supercomputer for about 9 days to run a reactive chemical simulation with 22 million atoms, almost 23 million atoms, using the ANI-RX potential. And this simulation started with water, oxygen, methane, carbon dioxide, and ammonia. And he ran for 4 nanoseconds at 2500 Kelvin. And we were able to find that these things didn't stay in these starting components for very long. We were able to form amino acids, sugars, and much more using ANI as the potential model to sample new chemical space. And this is, it has nothing on like the GDB data set or something that's, you know, just an enumeration of every molecule that could exist, but it's how we can use our model to produce new data that could help our model to improve. Now this figure isn't very scientific, but I think it looks pretty. This is just a diagram of the formation of an alanine molecule over time. I think this is 250 frames that I isolated. And this just shows sort of the path that each of the atoms take in order to associate into this alanine model. It's kind of hidden back here, but it shows just this, you know, high temperature simulation, how things randomly come together and associate. And most of what we started looking at from this simulation data was a pretty small list of molecules of interest that are bioactive molecules such as amino acids, sugars, but as I said before, there's much, much more that was produced, you know, synthesized in this reactive simulation. But of the products that we're looking for, this list of amino acids, most of the things that we found, which were identified via a graph search where, without going into too much detail about it in order to save time, we plotted every atom in every frame and found how far apart its nearest neighbors are. If they're within some distance threshold, then we consider those things to be bonded. It's not a perfect search, but it was very fast, and it actually ended up being pretty reliable as a means of getting new structures from all of this, you know, huge amount of data. The reaction trajectory takes up about 92 terabytes total, so it's, you know, an insane amount of data to try and parse through. But this is a list of the amino acids that we found that were formed. Most of them were glycine and alanine. If you filter those out, then we still have a few thousand miscellaneous structures that are, you know, novel to the ANI reaction simulation. And these are molecules that are you know, we have something that's similar to them in our data set, but we haven't sampled these sorts of conformations before, and this reaction data is a way to add new configurations into our training set. So over time, when the system was heating up, we went from starting at just a few atoms on average in the system up to, once it was at 2500 Kelvin, we hovered around 18 atoms was the average size of a molecule that was found in this simulation data. And then also another thing that we looked at was in each frame, and there are about 350,000 frames in this reaction data, what is the largest molecule that was found out of any of these connected components? And you know, this is a number that varies a lot, which means that there's a lot of interacting and changing and bonding that's going on. It's all very promising, but the cool thing is at some point there was a 96 atom molecule that was formed. And this is something that's much larger than we have in any of the ANI training sets, and this is a big work in progress. We haven't, you know, by any means pulled out all of these structures because, again, there's just so much data to look through, but this is what a lot of our effort has been going into recently. And you might be thinking these are just atoms, you know, floating around almost randomly. How can you really trust that the structures that are being formed are anything like real molecules? And so we first looked at alanine because there wasn't just an absurd number of them like the glycine molecules, but about 500,000 structures to try and pull out. And I took each of those structures, got the coordinates of them, and, you know, plotted the dihedral angles of them. And this distribution is about what you would expect from a large amount of like molecular mechanics sampling of a single alanine molecule, what conformations it would find itself in. We have, you know, a good distribution of conformations for at least alanine, and we're moving into looking at other molecules now. So to conclude, the big limiter of computational chemistry are cost limitations. We wish that we could use QM to solve every problem, but it's just not reasonable, and atomistic neural network potentials are great at predicting the total energy of a system. In order to improve those, we're hoping to find better ways to quantify the uncertainty on an atomistic basis and sample new structures based off of those predictions. And then we want to move more into these large-scale molecular mechanics simulations and show reactions actually occurring, showing the changing of bonding at a cost that's similar to that of molecular mechanics. This is a great thing, but there's, uncertainty prediction is necessary because there's no reference energy to know if these networks are right or wrong. You can't compute QM on 22 million atoms. It's impossible. But predictive uncertainty seems to be a good estimator of whether we're right or wrong. And so I want to thank my advisor, Dr. Adrian Reutberg, and my fellow group members. I want to thank the UF Department of Chemistry and Hypergator for the computing resources, and I want to thank the SciPy organizers and all of you for listening to my talk. I'd be happy to answer any questions you have.
Thank you, Nick. Are there any questions? Yes. And I'll repeat the question for the online audience.
So thank you. It was a very nice talk. So to my understanding, in the past 10 years, but also recently, there's been a huge effort in developing these neural network potentials, right? And there's a bunch of available machine learning interatomic potentials online, like ChargeNet, ANet, Maze. So my question is, what is the advantage and what are the disadvantages of using this AI potential with respect to nodes? Because to my understanding, they are more or less all based on the idea of a local atomistic environment, right? So
Thanks. Yeah, so just to rephrase briefly, there are a lot of neural network potentials. Many of those share ideas about how to construct this local environment. What makes any special or different from the others?
So this, is going to be a big picture general answer, but the thing that we pride ourselves on as ANI developers is the generalizability of the ANI model. The idea is that our atomic neural networks are capable of giving an energy prediction for any carbon atom. It's, we don't do anything specific with atom types, as in like hybridization states, or there's no real input of physics other than the data that we're training on. And there are some other models that do that. I'm not going to pretend that we're the only ones. But the generalizability, transferability, and the scaling of the ANI models is what we really pride ourselves on. I didn't show any of it here, but our training sets include atoms of things that range from 2 atom molecules up to about 60 atom molecules. And our testing sets, or our validation sets, contain molecules that have up to 300 or 400 atoms in them, and we're able to predict the energy of those things very well, despite never, actually training to molecules that large. And one thing I will say about other models is a lot of them tend to use the ANI training sets in order to, their architecture is different, but the data that they train on was produced by our group 5 or 6 years ago. And the other advantage is speed. That's the big one out of using neural network potentials, and also a lot of our recent developments in the Reutberg group have been to try and make the ANI potential just ever so slightly faster. That's through GPU acceleration, parallelizability, things like that. Yeah, thank you.
I actually also have many questions, but we are asked to keep the 10 minutes time frame for people to be able to move. So I would suggest we stop here and we just ask our kind speaker in person. Let's thank him again.
Thank you.
Thank you.